హలో స్టూడెంట్స్, వెల్కమ్ టు GNV లెర్నింగ్ పోర్టల్. ఈ ఛానల్ ద్వారా మనము ఎంఎస్సి ఫిజిక్స్ ఎంట్రన్స్ కోచింగ్, ఐసెట్ కోచింగ్, ఎస్బీఐ క్లర్క్స్, జూనియర్ అసోసియేట్ అలాగే ప్రిలిమ్స్ మెయిన్స్ కోచింగ్ గురించి తెలుసుకుంటుంటాం. సో ఈ వీడియోలో మనము ఎంఎస్సి ఫిజిక్స్ ఎంట్రన్స్ కోచింగ్లో భాగంగా థర్మల్ రేడియేషన్కి సంబంధించిన కొన్ని ప్రాక్టీస్ బిట్స్ చూద్దాము. అంటే ఎగ్జామినేషన్ పాయింట్ ఆఫ్ వ్యూలో ఈ థర్మల్ రేడియేషన్ కాన్సెప్ట్కి సంబంధించి మనకి బిట్స్ ఏ రకంగా ఇస్తూ ఉంటాడు అనేది మనం ఈ వీడియోలో తెలుసుకుందాము. సో ఆల్రెడీ మనం లాస్ట్ వీడియోలో థర్మల్ రేడియేషన్కి సంబంధించినటువంటి ముఖ్యమైన కాన్సెప్ట్స్ గురించి తెలుసుకున్నాము. సో ఫస్ట్ ఆఫ్ ఆల్ మనం ఫస్ట్ క్వశ్చన్ని కనుక చూస్తే, the wavelength of maximum energy in solar spectrum is 4753 angstroms and the value of Wein's constant is 0.293 centimeter degrees. So we have to find the effective temperature of the sun. So this question is based on Wein's displacement law. So if you know Wein's displacement law, we can easily answer this question. We know that Wein's displacement law is equal to lambda m into t is equal to b, where b is the Wein's constant that is already given in the problem itself. So what is the value of b? B is equal to 0.293 centimeter degrees. B value is given in degrees centigrade. So that is it was given in Celsius units. So next we have given the wavelength of maximum intensity, that is lambda m is equal to 4753 angstrom units. So it can be written either in centimeters or in meters, but b value is given in centimeters, so we have to write this in centimeters. So 4753 into 10 power minus 8 centimeters, because 10 power minus 8 centimeters is equals to 1 angstrom unit. It can also be written as 4753 into 10 power of minus 10 meters if b is given in meters. So now we have to find out the temperature of the sun. From this equation, T is equal to simply b by lambda m. So b is equal to 0.293 and divided by lambda m, 4753 into 10 power of minus 8. If you solve these terms, we have 0.00006165 into 10 power 8. If you take this power in term into above, it becomes 10 power 8. So that is equal to 6164.5. So temperature is equal to 6164.5 and this value is approximately equal to 6165 Kelvin. So that is equal to option A. So here there is a small confusion is given because the temperature is given in degree Celsius, but we get the answer in kelvins. It is not in degree Celsius. The temperature itself is in Kelvin scale. Why? Because if you take b value as 0.293 into 10 to the power of minus 2 meter Kelvin, so that is in MKS system. So if you take these two values also, we get the same value of temperature 6164.5 Kelvin. So that here degree means it is degree Kelvin. So not in degree Celsius. So to confuse the candidate or student, B value is given in Celsius system. So no need to change the temperature from whatever it may be the given degrees or Kelvin. We need not change the temperature into Kelvin into centigrade or centigrade into Kelvin. Whatever you get the answer is in Kelvin scale. So our option is 6165. So option A is the correct answer. So now let's go for the second question. So Rayleigh Jeans formula agrees for shorter wavelength region, infrared region, longer wavelength region, and microwave region. So in the earlier video we discussed about Rayleigh Jeans law. So this Rayleigh Jeans law is always agrees with longer wavelengths. So in longer wavelengths, we can use Rayleigh Jeans law to find out the energy of the black body. So directly we can answer this question as C, because it is used in longer wavelength regions, and Wein's law is used in shorter wavelength regions, and in all wavelength regions we use Planck's radiation law. So this is you have to identify that or differentiate between these three laws: Rayleigh Jeans law, Wein's law, and Planck's law. Now go for the next question. So in Wein's displacement law, the maximum intensity of radiation emitted is displaced towards. So earlier we discussed in the previous question, the Rayleigh Jeans law is for longer wavelength regions, and Wein's displacement law or Wein's law is used in shorter wavelength region, because when we are deriving that Wein's law or Rayleigh Jeans law, so they are limited to certain wavelength regions. So for smaller regions, Wein's law is acceptable, and for longer wavelengths, Rayleigh Jeans law is acceptable. So coming to the fourth question, the pyrometers are used for measurement of high pressure, low temperature, high temperature, and low pressure. Obviously, option C is the correct answer, because the pyrometers are used to determine or to measure the high temperatures, that to the temperatures of above 6,000 degrees Celsius. 6,000 degrees Celsius above temperatures measurement, we use only pyrometers. Next, so what is the value of solar constant? So we already know that the solar constant value is constant value on Earth. So that is equal to 1340 watt per meter square. Because the solar constant is different for different planets, but if in the problem they are given only solar constant value, so that means it is a solar constant value of Earth. So we need not any confusion. That means the solar constant of Earth, and the solar constant of Earth is 1340 watt per meter square. So option D is the correct answer. So next question is, determine the temperature of the sun with the help of Wein's law. So what the given Wein's constant B is equal to 2.92 into 10 to the power of -3 meter Kelvin, and the maximum wavelength of 4,900 angstrom units. So almost the questions based on Wein's law or Wein's displacement law, almost B value is approximately equal to 3, and the wavelength is around 5,000. So the answer is almost equal to 6,000, in and around 6,000 Kelvin. So when you are looks like the option will be option A, it's around 6,000, that is 5,900 or 5,970 or 6,000. So in and around about 10 to 100 Kelvin differences, we will get the answer in and around 6,000. Anyhow, we have to calculate the temperature. T is equal to B by lambda m. So here given B is equal to 2.92 into 10 power of minus 3. That was given in meters. So we have to write 4900 into 10 power of minus 10 meters. We have to write this wavelength in meters. So 10 power of minus 10 meters. So that is equal to 2.92 by 4900 into 10 power of minus 3 plus 10. So 2.92 by 49 into 10 power 7 minus 2, because these two gone. So 2.92 by 49 into 10 to the power of 5. It can also be written as, for simple calculation, 292 by 49 into 10 cube. So 292 by 49 292 by 49 is equal to 5.959 into 10 cube. So you have to easily calculate this. 292 divided by 49. So it is equal for 50. 50 into 6 is 300. So it should be 5 times 245. So 245 is 7 and it is 4. 470. Again it is gone point. So 9, 81 and 441 is 29, 290. Again it's 5 times 245. Another 45 is coming, 450. So again it is 9. So 441. So 9. So it is enough for us. So we have taken 5.959 into 10 cube. That means 5959 Kelvin. So the answer is 5959 Kelvin. So it is in and around 6,000 Kelvin. So when you are looking like this problem, so we can easily tick that option. But here is a problem is another 6240. So we have, so that we have to calculate this. So option A is the correct answer for this problem. So for the next question, again given the radiation pyrometers are used to measure the temperatures. So here the radiation pyrometers means total radiation pyrometers or optical radiation pyrometers, whatever it may be. Already we have discussed in the earlier questions. The pyrometers are always used to measure the temperatures of values greater than 6,000 degrees Celsius. But here in these options, they given only 200 degrees Celsius, 500 degrees Celsius, and between 500 to 1000, above 1000. So the only option we have to tick is above 1000 degree Celsius. So next question, if the solar constant on the earth is 2 calorie per minute per centimeter square, then the solar constant on Mars, which is at a distance of 0.4 times that of the earth from the sun. So given in this problem, given the solar constant of earth, that is equal to 2. What we have to calculate? The solar constant of Mars. Solar constant of Mars we have to calculate. So the relation between, and given that for this they have given that the distance between Sun and Mars, the distance between Sun and Mars is how many times that of the distance between Earth and Sun? It is 0.4 times. That is here small r, that is Re. If Re is the distance between Earth and the Sun, then Rm Rm is the distance between the Mars and Sun. It is equal to 0.4 into Re. So that is given in the problem. So we have to find out Sm, that is solar constant on Mars. So the relation between Sm and Rm is very simple. Se, because the total radiation is equal to S into R by R whole square. So this is the formula. The total radiation is equal to, or the total energy emitted is equal to S, that is solar constant, to small r by capital R whole square, where R is the distance between the Sun and the planet and capital R is the radius of the Sun. So these are the given. So that what we have to conclude from this formula, S into R square is equal to constant. Because here in these two situations, Sun is constant. So kabatti R is constant and E is also constant. So SR square is constant. Hence, SE square is equal to SM RM square. SE square is equal to SM. What is RM? 0.4 whole square into Re square. Re square is cancelled. So Sm, that is solar constant of Mars, is equal to Se by 0.4 whole square. So 2 by 0.16, 200 by 16, it can be written as, or 12.5. So here in the options we have 12.5 is option A. So option A is the correct answer. So solar constant on Mars is 12.5. So coming to the next question, again in an atomic explosion, the maximum temperature produced is of the order of 10 power 7 Kelvin. So here in this problem, the temperature is given, that is equal to 10 to the power of 7 Kelvin. And also given the Wein's constant is B is equal to 0.292 centimeter Kelvin. What we have to find? The maximum energy wavelength, that is lambda m, we have to find. So lambda m is equal to B by T. So 0.292, that is in centimeters, 10 power 7. So 0.292 into 10 power 7 centimeters, 10 power minus 7 centimeters. So 10 power minus 7 means, if you have, the options are given in angstrom units, so that you have to convert this into angstrom units. So 2.92 into 10 power minus 8 centimeters. So 10 power minus 8 centimeters is equal to 1 angstrom unit. So the answer is 2.92 angstrom units, and option A is the correct answer. Sorry, option 2.92 angstrom units. So option C is the correct answer. So coming to the next question. So what is the spectrum obtained by the black body? So it is a line spectrum or band spectrum, continuous spectrum or absorption spectrum. So only continuous spectrum. The spectrum obtained by the black body is continuous spectrum, because the spectrum of black body ranges from wavelength 0 to infinity. So that the energies also ranges from 0 to infinity. Hence, the spectrum of the black body radiation is a continuous spectrum. It has all types of energies and all ranges of wavelength. So next question, the velocity of heat radiation in vacuum. So this is also easy question. The velocity of heat radiation in vacuum, because heat radiation is obeys light properties. Hence, the velocity of heat radiation is equal to velocity of light in vacuum. So option B is the correct answer. So the final question, the radiant energy in Stefan Boltzmann law is directly proportional to. So we know Stefan Boltzmann law E is equal to sigma T1 power 4 minus T2 power 4, or Stefan's law E is equal to sigma T power 4. Anyhow, the energy of the radiation is equal to fourth power of its temperature. Hence, option D, T power 4 is the correct answer. So these are the main important bits that are given in examinations. So follow these questions. If you have any doubts or queries, post in comment box. So in the next video, we will discuss quantum theory of radiation and practice based on the quantum theory of radiation. Thank you.